In this video, we will introduce the concept of functions, what constitutes a function, and the terms that are commonly used in functions. Firstly, what is a function? We can think of a function as a machine. For example, let's think of a function as a juice pressing machine. This juice press takes in certain inputs, for example, a lemon, and transforms it into a lemonade. Likewise, it can also transform an orange into a cup of orange juice. So the lemon and orange are the inputs to the machine, which then gives us the juices as the output. Now, imagine if we instead use a durian as an input, will we be able to get any output? The answer is no, since the machine is not made for such purposes. So from this, we know that functions require specific inputs, which we call domain, to give us a certain output called the range of the function. If we put numbers to this function, what it means is that some functions will not be able to take all real numbers as its domain. Thus, it is important that when we define a function, we always define the corresponding domain. The range is not essential in the definition of a function, as it can be derived from the function and its corresponding domain. Whenever we define a function, it is always given in similar form, as shown in this first line. It is a standard presentation format which says that the function f maps x into the expression of x squared plus 1 for the corresponding domain of x between -2 to 1 inclusive. As mentioned earlier, we must always include the domain whenever we define a function. Also, for calculation purposes, it is usually more convenient to convert the function from similar form into equation form, which is written in this second line over here. So how we can write it is f bracket x, which means f of x equals to x squared plus 1, and we have to give the corresponding domain of -2 less than or equals to x less than or equals to 1. So this is the equation form of a function. Note that we must also include the domain after we convert into the equation form. To find the range of a function, we can simply sketch the graph of the function out. So for the function given above, we can sketch the graph to be like this, where the black dotted line actually shows the entire graph if there is no domain restriction, but due to the domain restriction, we have to restrict the graph to the red color portion over here. So the domain of this graph is actually from -2 to 1, and correspondingly we will be able to extract the range from this graph, which is from this minimum point all the way to this highest point where all the y values are being covered. So in this case, we know that the minimum point occurs when x is equals to 0, and this gives us f0 equals to 1, and the highest point occurs at -2, so f -2 gives us 5, and therefore we can say that the range of function f must be equals to 1, 5. Let us now look at some examples of finding the range of a function. In example 1a, we have the function fx equals to x for all real values of x. So if we sketch the graph out, it will look like this. And to get the range of this function, we try to find out what are the y values that the graph covers. So we can see that it is going to be covered from 0 all the way up until infinity. And we know that the range of this function is going to range from 0 to infinity. And how we are going to present the range is R, capital R, meaning range, subscript f. So we have range of f equals to a round bracket 0, infinity, and a round bracket again. So why do I use a round bracket now as opposed to a pair of square brackets in the earlier slide? This is because for round brackets, what it means is we do not include the endpoints. Whereas for square bracket, we will include the endpoints. So let's say I have an example of minus 3 smaller than or equals to x smaller than 2. I can write this in set notation form to be square bracket of negative 3 because I want to include negative 3 due to the equal sign, comma 2, but I do not want to include the value of 2. I will end off with a round bracket. In example 1b, we have the same definition of function f, but there is a different domain now. So if we draw the graph, it will be a part of the graph that we have drawn earlier. So it looks like this. Instead of going from minus infinity to positive infinity, we are just going to go from minus infinity all the way to 0, excluding 0 because we are looking at all real negative numbers. And from this graph, we can see that the range is going to be ranging from 0 all the way to 1. And we can therefore write the range of the function f now as Rf equals to round bracket 0, comma 1 round bracket because we are not going to include both endpoints. In the earlier examples, we can simply take the n values of x and substitute them into the function to get the range of the function. But do take note that this is not always the case, as we will see in this current example. For the graph of fx equals to x squared minus 2x plus 3, we can complete the square to give us x minus 1 squared plus 2. And therefore, we know that the minimum point of this graph is going to be at the point 1, 2. And let's draw the graph out. Starting from x equals to 0, because we are looking at all real positive numbers. When x is 0, we have y equals to 3. So it's somewhere over here. Okay, and we are going to have a quadratic graph that goes this way and up. And this minimum point over here is 1, 2. And therefore, if we are going to just make use of the endpoints, which is 3 and infinity, as the endpoints of the range of values of this function, we are not going to get the correct function because there is this portion that we are going to miss out. Therefore, we have to be careful whether there is another minimum or maximum point in between our domain that we have to take note of when determining the function's range. And therefore, this gives us the range of function f to be from 2 all the way to infinity instead of 3 to infinity. It is a common misconception that functions and equations are the same thing, but there is a distinct difference between these two terms. Take for example, if we have the curve of y equals x squared, which looks like this, we can say that y equals x squared is a function. However, if I have a circle which has equation of x squared plus y squared equals to 1 and the curve looks like this circle is not a function, but it is an equation described by x squared plus y squared equals to 1. The difference lies in the fact that for functions, one input can only give us one output. So if we look at y equals x squared, at every x value, there is only one corresponding y value. Whereas for the circle, at every x value, it gives us two corresponding y values, which therefore violates the condition and definition of a function, and this equation of a circle cannot be considered a function. However, the reverse is not true. It is okay for one y value to have come from two different x values. So for example, if I had y equals x squared, if I look at a particular y value, there will be two corresponding x values. It is perfectly fine for this to be considered a function. Based on the definition of a function, we can perform a simple vertical line test to determine if a given curve is a function. If we are going to draw a random vertical line across any given curve, and the vertical line cuts the curve at most one point, then the curve is considered a function. If the vertical line cuts the curve at more than one point, the curve is not a function. For example, let's take a look at these three curves below. For the curve on the left, if we draw a vertical line everywhere, you see that all the vertical lines only cut the curve at exactly one point, and therefore this is a function. For the curve in the middle, if you are going to draw a vertical line anywhere, it is also going to cut the curve at exactly just one point at most, and therefore this is also a function. Finally, for the curve on the right, whenever we draw a vertical line, it is going to cut the curve at 2 points. And therefore, we know that this is not a function. Once we establish that a given graph is a function, the next step is to further classify the graphs. For the graph on the left, we observe that for every y value, there is only exactly one x value, meaning that every xy relationship is a unique one. We call this type of function a one-one function. For the graph on the right, we see that for every y value, there are actually two x values. And therefore, although this is still a function, it is not a one-one function because two x values can give us the same y value. This is thus called a two-one function. The concept of a one-one function will be important in the next lesson when we are dealing with inverse functions.